Hello students, we are in the flood module of Concord Consortium. We're on lesson 2 and we're starting on page 5. This is part 2 of lesson 2. Let's look at the water model. When precipitation falls, it adds water to the ground. What about the water that's already there? Even though you can't see it, it's likely that the ground beneath you already contains some water. If you're close to a river and dig down far enough, you'll eventually find the level that is saturated with water. You've probably seen this at the beach. If you dug a hole in the sand, eventually there's probably water at the bottom of your hole. Now you will investigate another factor in the flood diamond, that's water table. The water table marks the surface of the water. It's visible in rivers, but not visible when it's underground. The level of the water table can vary depending on several factors. How does precipitation affect the water table in and around the river? Run the model below and try different starting water levels. So let's start low and just run a whole bunch of rain in there. And if the starting level is low, it takes a lot of rain to kind of fill up the water table and overflow the river. You can see that here's something that represents a low water table. It has a lot of room in this glass here before it overflows. You can add a lot of water here before this glass overflows. If the water table is high because of snow melt or previous rainfall, you don't have much room here to add water to this river before it starts to flood. So here's low water table, here's high water table. You can see very easily that high water table here doesn't have a lot of room for extra water from either snow melt or precipitation to add before it overflows, or floods, as we say in a river. You can see that it's raining and raining and raining and raining, and the water table is starting to come up here in our model. We can follow a couple water droplets here. They're just going right in. Let's follow another one here. Falls, sinks, percolates down through the ground. That means kind of flows very slowly, gets kind of bounced around, and then becomes part of the water in the water table. And you can see as it continues to rain, even though the water table was low, it's raining and raining, and in the Midwest, the snow melting and water running off surfaces because of snow melt contributes to a river flooding. And here we go. Our river is flooded, but it took quite a while to get a lot of rain to get this river to flood. So let's take a snapshot here. And if you're having trouble with the snapshot feature for some reason, just hit refresh on your in your browser. I forgot to hit stop here. I have to hit stop, and then I can take a snapshot. So if for some reason it isn't taking a snapshot, circling the water table seems kind of silly here, so I'm going to draw a line where the water table is. It's above the whole river system right now. It rained and rained and rained. It's time to get your boat out here, even if you live on land. Using the snapshot, explain why rain can no longer be absorbed into the ground when flooding occurs. Well, the level of where rain would be absorbed is above where land is. So the water table is now above where the edges of the river are. So the water goes over the riverbank and floods. Basically, we've kept adding water and adding water and adding water until the glass is overflowing, or in this case, the river is overflowing. The water table is a factor in the flood diamond. How does the height of the water table contribute to the likelihood of flooding? Well, while we're thinking about question 20, let's refresh this model here. Let's still have it rain a lot, but let's have the starting water level be high. And this time, I bet it won't take as long to flood. So we'll keep an eye on that while it's raining. So here's the water table right here. The water table is the level of the river, in the river, but the water table outside the river is just where the ground is saturated. If you dig down right after the snow melts here in Minnesota, it's probably going to find a lot of the soil is saturated. The water table is really high because so much water is soaked into the soil, it really can't take any more. And that's when there's a lot of danger of flooding. If it rains on top of all that snow melt, the ground's already saturated, it's already full, and if you add a little bit more, it's going to flood. So the more, well, let's just say the higher the water table, the less rain you need to add to get flooding. Just like I don't need to pour much water in this glass before it overflows. It's already pretty much full, and this would be a high water table in spring. This would be more kind of like a summer water table where it's been hot and dry for a while and there's not so much water either in the river or in the soil around the river. All right, the rivers shown in the Flood Explorer have 3 stream gauges. Gauge 1 is shown on undeveloped land. Gauge 2 is shown near Hidden Valley Farm. We'll take a look at these in a bit. Gauge 3 is located near the edge of Silverton. So here's 1, 2, and 3, and they have tabs here, 1, 2, and 3. At each stream gauge, you can see a cross-section of the river in the Flood Explorer. You can use the cross-section views to see how the height of the water table changes. As it rains, the water table changes. In the cross-section view of each gauge, the blue-colored area shows the water underground, and the dark blue line is the top of the water table. Watch the video below to learn about the stream gauges in Flood Explorer.
The Flood Explorer includes 3 stream gauges spread out across the Silverton region. The stream gauges on the map are indicated by a colored dashed line extending across the river. You can see them here, here, and here. Each stream gauge has an associated cross-sectional view of the river at that location in the right-hand side of the model. The left side of the cross-sectional view is indicated by the dot and label of the stream gauge on the map. For example, at stream gauge 3, you can see a park on the left side of the cross-section and stores on the right side. Those are indicated by the green area on the map and the roads on the map. The stream gauge shows exactly what is happening in the river at all times. In each stream gauge tab on the right, you can also see a river stage versus time graph for the stream gauge. This gauge shows the level of the water table. I'll start a rainstorm so you can see the level of the water table rise in the cross-section. A flood occurs when the water in the river overruns the banks. The red line on the river stage versus time graph shows the level at which the river will flood at each stream gauge. When the blue line goes above the red line, the area at the stream gauge is flooded. Be sure to carefully observe the shape of the river and the flood level at each stream gauge.
Okay, so that's about stream gauges. Let's investigate how starting water levels affect the likelihood of flooding in the 3 areas where the stream gauges are installed. First, set the amount of rain to heavy and storm duration to medium. Then run the model 3 times with different starting water levels for low, medium, and high. Examine the stream gauges in all 3 locations and under all 3 conditions. So, amount of rain heavy, storm duration medium, starting water level low, and we're going to be watching the stream gauges here to see if there's any flooding. You can see gauge 1, it just barely ran over the banks for a little bit. Gauge 2, it didn't get up to the level where it would flood. It maybe came just right up to the edge right here. And in gauge 3, it didn't even get close to the top of the riverbanks, and it just went right down. So I'm going to stop this. So let's make water level medium here. We'll reload. Water level medium. Storm duration long. Amount of rain heavy. Let's look at gauge 1. Oh, there's some flooding. You can see it flooding into the trees here. Let's look at gauge 2. Yep, it went up over the banks. Gauge 3, yep, looks like there was a little bit of flooding there. Let's back it up here so we can see what flooding. You can see the soil saturating, and then you can see it flooded here. This is the soil, and when it creeps up you can kind of see the soil saturating here. The soil on both sides of the banks of the river is saturated up to about this level. As the storm continues, more and more rain gets absorbed by the soil, and eventually the soil can't hold anymore, and the river level fills up, and you've got a flood. And that's what happened here. It went over the banks, and we know it went over the banks because this level here, flood stage, like I think it's about 28 feet, is where the river floods. Let's reload. Let's do starting water level high, storm duration long, amount of rain medium. And just make a prediction in your head. If the starting water level is high, how's that going to be different? How much rain do we need to add before we get a flood? There was some even flooded at gauge 3. So when starting water level is low, which areas are likely to flood? Well, we didn't get any floods when the starting water level was low. When the starting water level is high, which are likely to flood? Well, we got a little bit of flooding at gauge gauge 3, but we got a lot of flooding at gauge 1, and we got mostly at gauge 1. Which area would be the highest risk of flood damage when water level is medium? Consider both the likelihood of flooding and the damage flooding can cause in the area. Well, if the water level is medium here, we know that the town is probably not going to flood, because when we look at gauge 3, the water level needs to be at 28 feet to flood the town. They put the town on high ground for a reason, because it doesn't flood as often, as easily. Gauge 2 doesn't flood as much. There's a farm there, and you want to put your farm and your cows and your barn on higher ground. Gauge 1 is an undeveloped area. It's a forest. They've left it a forest because they know it's going to flood. If you're a good city planner, you leave areas that are very prone to flooding as parks or open space. So if they do flood, it's not a big problem. So the undeveloped area is going to be at the highest risk of flooding. And I'm just going to take a snapshot. We had water level medium here, storm duration long, amount of rain medium, and we did get flooding here at gauge 1. So I took a snapshot, saved it, used the snapshot to explain question 23. Well, I know that the gauge, this gauge, the flood stage is 14 feet. The flood stage of the river at gauge 1 is 14 feet. When I look at other gauges, I see gauge 2 is, I think, 15 feet. Let's look again here. If I click on the gauge 2 tab and look on the graph here, the purple line here that shows when the river is going to overflow its banks is at 15 feet. So gauge 2 is 15 feet. And gauge 3, that's on pretty high ground. I believe gauge 3 is like 27 feet. 28. So gauge 3 is at 28 feet. I can see that because I see the red line. The red line at this gauge represents how high the water has to be to flood that part of the river. And 28 is a lot more than 14 or 15. The town is on higher ground. More where the river has higher banks. The town is least likely to flood. The undeveloped kind of woods area, the forest, is the most likely to flood because it's got a flood stage of 14 feet. And I know that from looking, if I click on the yellow tab and I look at the yellow line on the graph, it's at 14 feet. How certain are you that the areas you chose the area you chose is likely to experience the high risk of flooding damage based on your model? I'm pretty certain. Flood gauges are pretty accurate. They are based on Historical data, flood models usually take into account many factors, including those in the flood diamond. Remember, precipitation, permeability, topography, and water table. And others, including information from gauging stations. And if you want to know where a gauging station is in your neighborhood, this is the USGS National Water Dashboard. So the USGS, the United States Geographical Service, has gauging stations all over the country and is monitoring river levels all over the United States. And you can zoom in. Here's the Mississippi River at Red Wing, Minnesota. There's a gauging station there that helps folks who are driving barges up and down the Mississippi. Also, any paddlers who might want to go out paddling on the Mississippi, make sure it's safe and has enough water to float a canoe. You can zoom in on your state, and it's easier to find those gauging stations. There are many more gauging stations on local rivers. They may not be monitored by the USGS. There's lots of information on if you go to paddling websites or maybe flood alert websites. The USGS also has a monitoring program where you can sign up for alerts if an area is going to flood. But here's gauging stations in real life. They're monitoring the Mississippi at all times. It's a big river, has a lot of shipping traffic, and so they tend to keep a close eye on that one. They're also monitoring other rivers that feed into the Mississippi because that helps them construct a flood model for the Mississippi. All right, let's go to page 7. So, Turkey River. We'll now return to the tragic flooding of the Turkey River. You've now seen how 3 of the factors in the flood diamond, precipitation, topography, and water table, influence the likelihood of flooding. Using what you know now, analyze the occurrence of flooding in the Turkey River. What could have caused the Turkey River to flood to a 500-year level 4 times in 27 years? The area received a higher than normal amount of rain. The topography in the area changed. Did they put in some hills? Did they take out a mountain? The water table was higher than normal. That can happen if there's a large snowmelt. The weather was much colder in the years of bad flooding. You can check the ones you think are correct and check your answer with that box. Based on the number of large floods in the recent past, do you think it's likely that the Turkey River will have another 500-year flood soon? Well, knowing now what you know about precipitation, that the Midwest is getting more precipitation, and the Turkey River in Iowa is in the Midwest, and that precipitation is causing more floods, that's a pretty good indication that the Turkey River might continue to fill up with rain because there is more rain. And there might be some more snow too, and snow melting tends to saturate the soil, raise the water table, and that can contribute to flooding as well. So you can write your answer, why you think or why you don't think the Turkey River will have another 500-year flood in the next 5 to 10 years. And then you can go on to lesson 3. I'll see you in lesson 3.